Bienvenidos, Ushamdi, and welcome CTS230 Section 841 students for the first 8-week term of the fall 2017 semester, which is actually concluding next week. This is the Networking 3 or the Scaling Networks V6 course from Cisco Networking Academy. And this morning's video tutorial and solution set is going to be on Packet Tracer Activity 10.1.1.12, where we're going to have an in-depth conversation here. We're going to go well beyond the scope of the activity to discuss the designated router and the backup designated router and what exactly do the DR and the BDR do? Why do we need them? How did they come into existence? And how do we go about influencing the selection of either the DR or the BDR? So let's go ahead right now and take a look at our activity here. Very straightforward setup. We've got 3 routers, router A, B, and C. You can see that the loopback addresses have been identified for us, and then we've got a shared multi-access Ethernet segment. And this is critical because remember, on point-to-point links, there is no DR-BDR election. So over a serial connection, you would not have a DR-BDR election on a simple point-to-point link. And the reason for this is that there can only be 2 things on that point-to-point link. So therefore, we don't need some sort of an optimization or an abstraction type of approach. And I'll talk more about that word abstraction. And that's really what the DR and the BDR are providing, as a layer of abstraction from the multi-access segment. So in this activity, we're simply going to walk through and do some DR and BDR work. Now, very important here, it says wait till the amber link lights turn green. Now, we've got the 50 seconds for the switches to come up. We can click fast forward, but we're not going to do that because our links are already green. So now we're going to verify the current OSPF neighbor states. So use the appropriate command on each router to examine the current DR and BDR. So, whoops, let's go to the CLI here on router A, and let's give ourselves a little more room to work with, especially lengthwise here. And you can see we've got our syslog messages, right, from the OSPF facility, severity 5, notification, and then a mnemonic here, adjacency change. So what's the OSPF process ID? It's process ID 1. And here are the 2 neighbors. Now, these are not the IP addresses that we will reach these neighbors on. What is that? Exactly, that's the router ID. And the router ID plays a part here when we're talking about the selection of who the DR is going to be. So on router A, let's go from user exec with the enable command to privilege exec. And actually, we'll hang here at privilege exec. So let's say show IP OSPF neighbor. These commands that we're running here with OSPF definitely need to be committed to memory, right? Definitely need to have these committed to memory to be able to recall them right away. So show IP OSPF neighbor. Let's go ahead and break out our pin tool here and take a look at what we've got. So we have the first entry here, which it says neighbor ID. Now remember, the neighbor ID is the router ID, the OSPF router ID. And as we've said before, this is not an IP address. It has the same format as an IP address and can even be derived, right, or assigned from an IP configured on the router, but when it serves as the router ID, in this capacity, in this context, this is a router ID. Now, what is the priority on the segment here with that router, 31.22, which will be router 2, as you can see right here from the loopback address. And so in this case, you can see where the loopback address has been selected as the router ID, and we have our default priority on a multi-access segment. So we are fully adjacent with router 2. And the reason that we are fully adjacent with router 2 is because, as we can see here, router 2 is the BDR, right? Now here's our dead timer, which we know to be 4 times the hello timer. So by default, the hello interval is 10 seconds. And then the dead timer, if we extrapolate that and multiply the hello interval by 4, we get 40. And this is changing constantly between 40 all the way down to 30, and then it goes right back up because we're receiving those hellos every 10 seconds. Now we see the IP address of the neighbor, right, of this router here, router 2. That is the actual IP address out that interface that we can use to reach this neighbor, this OSPF neighbor. And so again, remember, that could be an IP address, but it doesn't have to be derived from an IP. It happens to be using the loopback interface. Because remember, how does OSPF select the router ID? And this is critical. Remember, OSPF selects the router ID. Number one, is it manually configured? And I'll just put man config. And that's with that router ID command under the OSPF global configuration section. Now, if you don't manually configure it, OSPF, when it starts up, is going to look for the highest IP'd loopback address. And so what does that mean? Does that mean if I had, interface loopback 99 and interface loopback 3, that it would pick 99? No, that is not what that means. And this is, again, very key point here. It's the loopback with the highest IP, right? So it's the highest IP'd loopback. Not the number of the loopback, the IP address of the loopback. Because if loopback 99 was 1.1.1.1 and loopback 3 is 3.3.3.3, and these are on the same router and OSPF starts up, which value is going to be selected as the router ID? Exactly, it's going to be loopback 3 because it has a higher IP address than loopback 99. So if it's not manually configured with the router ID command under the OSPF global config section, and if there are no loopback addresses, then what happens? Exactly. Then it goes to the interface with the highest IP that is up, right? So again, it's going to look for the interface with the highest, and again, IPv4. I didn't write v4 in here, but it's IPv4, because even when we're talking about OSPF version 3, which is OSPF for IPv6, what we end up with is we have to have an IPv4 address. And so here are the 3 setups that we have right here, or the 3 choices in the order that they occur, which is manually configured. It would take that over these 2. If there's not manually configured for a router, if it's router's not configured manually for a router ID, we go to the highest IP on any loopback. Then we go to the highest IP on any interface that is up. And so that is why these have been selected. These 2 values here have been selected as the OSPF neighbor ID, which is literally the router ID, and that is what they are using for their value. Now, this becomes important as we transition the conversation to the designated router, right? Because the designated router is also concerned with the router ID value, but it'll be after the priority. So the appropriate command to examine the current DR and BDR is show IP OSPF neighbor. Which router is the DR? Well, we can see here because that is showing me the state of the neighbor, right? This is neighbor information here, okay? And so router 3 with a priority of 2 has been elected as the DR. So router 3 is the designated router. Which router is the BDR? Again, we can see here we are fully adjacent to the BDR, and this is also important. Remember, if this is the DR and this is the BDR, router A would be seen if there was, if there were other routers over here, let's say router X, right? Router X, they would be seen as druthers, D-R-O-T-H-E-R-S, or DR others, because if you are not the DR and you are not the BDR, you are a druther, right? And so in terms of DR, BDR status, these two guys, X and A, druther, D-R-O-T-H-E-R, pin tool's not cooperating here. So these two guys would see each other as druthers. And they also would not come into the full state with each other. They would settle into the two-way state. And the book does a very good job of pointing out the difference between being adjacent, right, and being neighbors. These two guys here would be neighbors. They would know about each other because they would see multicast packets that are out there. So they would know about each other, but they would not be fully adjacent. They would stop in the two-way state. But they would both be fully adjacent with the DR and the BDR. Okay? And so this brings up that equation that we talk about. It's the n times n minus 1 divided by 2. And this is the entire reason behind OSPF, as well as the other link state routing protocol, which is IS-IS, which was developed by ISO, the International Standards Organization. And they are link state routing protocols. And the reason that they struggle with multi-access segments, and when I mean struggle, I don't mean from an operational perspective, but from a database and a flooding perspective, there had to be some sort of fix, right, or some sort of methodology to limit the number of adjacencies, because with 3 routers, it's not that big of a deal, right? We're talking about 3 times 2 divided by 2. So if everybody had to be adjacent with everybody else and we had 3 routers, you'd only be looking at 3 full adjacencies. When we talk about 50 routers, right, and 50 minus 1 is 49, and I don't even know what that is going to work out to. But if you were to do the math, let's go to a smaller number here. Let's go to 10. So if we had 10 routers, and we said 10 times 9 divided by 2, you'd now be maintaining 45 adjacencies, right? Or there would be 45 adjacencies being maintained, full adjacencies. And then you would have link state acknowledgement packets that would have to go to all 10 neighbors, or all, I say if there's 10 routers, to all 9 neighbors. And it would just be ridiculous in terms of the amount of flooding that would be taking place of link state packets, right? As well as the number of adjacencies that would be maintained. And so both IS-IS and OSPF implement the concept of the DR and the BDR. And so I'm going to take you real quickly here to, we've got the ISO standard there, and let me slide this guy down just a little bit out of the way. And I want to take you, this is the John T. Moy book. And remember, we talked about this text. I'll show you the cover here in a second. But take a look, right? It talks about the Bolt-Beranek company had converted the ARPANET link state protocol to a TCP/IP protocol, but the protocol was too inefficient. So at the same time that we were developing OSPF for TCP/IP, the ISO standards organizations were developing a link state routing protocol called IS-IS for the OSI protocol stack. And remember, that's the OSI reference model, right? We refer to it all the time. The physical, the data link, the network, the transport, application session presentation, the 7-layer OSI model. And so the organization, which was called ISO, that gave us that 7-layer model, also gave us the IS-IS link state routing protocol. And so take a look here. The emerging IS-IS protocol had already developed an efficient mechanism for running link state protocols over broadcast links such as Ethernet LANs, just like the one that we are looking at. And so it was ISO, the ISO, in the development of IS-IS, which is intermediate system to intermediate system, and an intermediate system is just a router. You could think of it as like R to R, right? Router to router. How are we routing traffic? They came up with this concept called the designated router, although technically in IS-IS it's not called the designated router, it's called a designated intermediate system. But again, you kind of, technically correct, but splitting hairs, right? It's a designated router because an intermediate system is synonymous with a router. But in ISO, IS to IS speak, it's a designated intermediate system. So they had the concept already to control flooding and perform information reduction. Because imagine the duplication of information on a LAN segment where everybody has to have the same link state database already. So really, only one router could be put in charge of the flooding of link state information. And in fact, that's the entire history of the DR and then the backup designated router. And a quick side note is IS-IS does not elect a backup, right? But we're worried about OSPF here. So again, John Moy knew that the ISO in the development of IS-IS had already come up with a concept, right? A method in which to handle the excessive flooding, right? And to reduce the amount of information that was going to be multicasted out on a broadcast segment, right? And this is the whole idea here, is that in a point-to-point configuration, again, I hope you can see why you don't need a DR and a BDR. Because there is no excessive flooding. You don't have multiple participants, or I should say more than 2 participants on a point-to-point link. You're limited to 2, and OSPF is fine with that, right? But on a multi-access segment, like a broadcast link, like an Ethernet LAN, so say you had 10 routers plugged into a switch, and they're all in the same VLAN running OSPF with each other, you end up with that n times n minus 1 divided by 2 in terms of the adjacencies. And then think about the link state database, how large that link state database would grow without the concept of the DR and the BDR. And so that's why we have the DR and the BDR. And the term that we used in class on Tuesday evening was to think of it as if it's a pseudo node. And so I'm going to stay here, and actually we're going to pop over to the RFC. So here is the RFC for OSPF 2328 OSPF version 2, and this is for IPv4, and you could take a look right here, right? John Moy 1998. Now I'm going to do a find here, and let's see, can I find pseudo node? No, there's no match for pseudo node. If I say pseudo, there's no match for pseudo. And so to explain where this term comes from, we have to again take a look back at IS to IS. And so this is in terms of the IETF, which was where OSPF was standardized, they call it RFC, right? Well, with ISO, they have the international standards, but it's 10589 was one of the original standards for IS to IS. And so when I do a Control F and I go to find pseudonode here, right? Take a look. The designated IS, the designated intermediate system, which translates in OSPF speak to designated router. So the intermediate system on a LAN, which is designated to perform additional duties. In particular, it generates link state PDUs, right, or the link state packets, as the text is referring to them, on behalf of all of the OSPF speakers on the LAN. And it treats the LAN as a pseudonode. And so this is where that term comes from. Again, the entire concept of the designated router comes from IS-IS, the other link state, and it's commonly referred to as the quote-unquote the other link state routing protocol. But to be honest, IS to IS is dominant in the service provider space. And then here's a great definition of pseudonode right here, where a broadcast subnetwork has connected intermediate systems. The broadcast subnetwork itself is considered to be a pseudonode. And again, it goes on and gives you some additional information here, but it gives you a nice, this is the reduction, right? Here's the reduction, because the picture here on the left in figure 1, down on the bottom, shows the full adjacencies that would be required with just 4 routers, like we're looking at right now. So this router here, let's say this is A, would need to become adjacent with him, and with her, and with him, right? Whereas, and in terms of the updates, the same thing, right? We're sending updates out and everybody's having to participate in it. And then these routers here, these 3 guys over here, we'll say it's B, C, and D, they need to become adjacent with everybody else as well. But with the pseudonode, the designated router is what that pseudonode is, right? It doesn't exist. It's virtual. Think of it as like a virtual machine, like with VMware, and we can move it from router to router if we so choose. We can influence whom is going to be the designated router on that segment, right? So the pseudonode is this virtual concept, and it's the same thing. The designated router, it's a virtual concept. It resides on one of the routers, right? And it can reside on any of the routers that are participating on this multi-access segment, but it's only on one of them at a time. And that router has the additional duty of serving up the virtual pseudonode or the virtual designated router. And it's with that virtual designated router that everybody becomes adjacent with. So he's adjacent with that one, with the pseudonode, that guy's adjacent with the pseudonode. Here you go. So there are your full adjacencies, right? And I won't talk about the E here, but we'll just say, pretend that that's an I for right now. These are all routers. So again, everybody is fully adjacent with the pseudonode. Now the pseudonode, remember, it's virtual. The cost of the pseudonode interfaces is 0, right? And so it doesn't add anything to the calculation. So whatever the outgoing interface cost is, and even if this is the DR, the interface, the cost of the outgoing interface on the node, right, on the actual router, that stays the same. That is what it is, depending on the speed of the link. The pseudonode is also not a hop. You don't have to go through the pseudonode. The pseudonode is here to provide information reduction. And I'm going to talk about the abstraction part as well. But it reduces the amount of information that's required to be flooded on a multi-access segment. And so hopefully you've got a good understanding now as to where this term pseudonode comes from, where it originated, how John Moy and the team that developed OSPF, where the entire concept of a designated router came from. So when we talk about, IS-IS and OSPF and the chicken or the egg, it was definitely IS-IS was the chicken and gave us the egg of the pseudonode, the DR, which we now see in OSPF. So let's transition now back to the activity. And so that is why in a multi-access segment, one of these guys is going to be our DR. Now we know that that's router C right now. So turn on IP-OSPF adjacency debugging on routers A and B. So let's make that happen. So we'll go from user exec to privilege exec. We're going to say debug IP-OSPF adjacency. And let's do the same thing here on router B. We'll get to the CLI. And we'll say debug IP-OSPF adjacency. And we're going to monitor the election process. So disable the link between router C and the switch to cause roles to change. And so now we're going to see what happens when the DR, the current DR, in fact, if I were to say show IP-OSPF neighbor here, right, you can see router 2 sees router 3 as the DR. Or I'm sorry, I say router 3, I mean router C. So we'll pop up here to router C. And we'll get into privilege exec, show IP interface brief. I think it's gig 00. Interface gig 00. Whoops, interface, getting global config, sorry about that. Interface gig 00. And we're simply going to say shut. Now, this should, and we didn't kick off our debug there, so let's pull router A back up. We've got adjacency debugging on here. And what did we see here? Debug IP-OSPF adjacency. Did we see anything? We didn't see anything on A, and we didn't see anything on B. So let's do this. Let's bring that interface back up, and let's see if that gives us any debug information here. All right, there we go, much better. So now we're seeing some information here in the debug. So let's take a look at that info. So we can see that the interface and actually, so important, it just dawned on me. So why did we not see anything immediately? Why did we have to wait? So you'll notice that that port was orange. So this is a great fortuitous failure. So, and this is where the dead timer comes into play. Remember, the dead interval, I should say, the dead interval is 4 times the hello interval. The hello interval's 10. So when I kill that interface right there, do routers A and B, do they realize that they've lost connectivity to C yet? No, they don't, because their connections into the switch here are up. So they think everything is just fine. However, we're going to be waiting for the dead interval to hit before A and B realize that C has gone away, because it's not a point-to-point connection between these 3 routers, right? In terms of C is not directly connected to A, it's not directly connected to B, so it's not recognizing the interface going down at a lower level. We're going to have to wait for OSPF to realize that it's gone. But here's what we saw, and this is what we were looking for. So you can see that if I were to scroll back, let's go back up here toward the top where we had the outage. And so this is where things start. And you can see we get an LSA is being built, right? Because it realizes that neighbor has gone away. So it builds its type 1 router LSA, which it's going to flood. And it's going to, this is where the election would take place, right? So it says DR BDR election is taking place on gig 00, and the BDR that gets elected is router 2, and this is also very important. The BDR is elected first. The BDR is elected before the DR, and the reason for that is that you want OSPF to behave the same way all the time. And so by electing the BDR first, we have consistency, right? Because you'll always have a BDR that gets elected. It gets elected first, and then it's the DR. And that's exactly what you're seeing right here, is that, yeah, router 2 says, yep, I'm the BDR. And then they look around and they say, well, you know what? I'm promoting myself to the DR based on the information in the hello packets that show the priorities, if any. And here you can see that at this point right here, router 2 is the DR, or becomes the DR. So now we go down here, we get another link state LSA that gets built here by router 1. So the BDR was elected first. Router 2, or router B, promotes itself to the DR, and then we have the election for who's going to take over the role of the BDR. And it turns out that router 1 gets elected as the BDR, as you can see right here, which means we now have LSAs that have to go out, right, from router 1, because it's updating its type 1 LSA, because now we know who the DR and the BDR are going to be. And that is what you see right there. So I have a series, I actually have 15 routers here that are plugged into a single Ethernet switch. And so we're going to go ahead and mirror the activity that we're looking at in Packet Tracer right now. So on router 1, I'm going to go from user exec to privilege exec into global config. I'm going to say router OSPF 1. Now remember that process ID is locally significant. And then I'm going to go to the fast Ethernet interface, which is where I'm running or going to run OSPF. I'm going to say IP OSPF 1 area 0. And David brought this up in class that he had kind of stumbled upon this command here in order to enable OSPF on a particular interface. And this is absolutely a valid command. It simply just isn't a command that's covered in the course. We talk about the network statements a lot, but I'm going to use this, which is sort of a shortcut to enabling the OSPF process on an interface. So we enable router 1. Let's go to router 2 and do the same thing. So we're going to global config router OSPF 1, interface fast Ethernet 00, IP OSPF 1 area 0. And then I'm going to go to router 3 and we're going to do the same thing. So I'm going to use 3 routers here as well. Oh, actually, we'll use 4. So router OSPF 1, and I'm going to say interface fast Ethernet 00, IP OSPF 1 area 0. And then on to router 4. We'll get into privilege exec global config, router OSPF 1. You'll notice I'm not setting the router ID here. And then we're simply going to say interface fast Ethernet 00, IP OSPF 1 area 0. Now, if I come back over to router 1, do we see any OSPF activity? Now, can I ping 10.0.0.0.2? I can. What about 3? So I've got full reachability and 4. So what should we see when I say do show IP OSPF neighbor? Well, we see that OSPF is kind of working its way through the finite, it's finite state machine, right? So everybody was down. When I entered the IP OSPF command, everybody went to init, right? And then we go to the two-way state, which you see there. And then you would go to EX start, EX exchange, loading, and then full. And so take a look here. And the reason I have 4 routers in here is I wanted to make sure I demonstrated the two-way drother, the two-way DR other. So here, who is the DR? The DR is router 4. And why is router 4 the DR? You'll notice the priorities are all 1. So it's the DR because it has the higher OSPF router ID, which just happens to be the loopback 0 address. They all have a loopback 0 address, routers 1 through 4, and it's simply the router number, right? So 4444 or 3333. And so the election took place. Router 4 is the winner, right? Router 4 ends up as the winner of the election to be the DR, the designated router. And so he will present the pseudo node. So if I say do show IP OSPF database, you can see we have the type 2 summary LSA. I'm sorry, I shouldn't say type 2 summary, sorry. Type 2 network LSA. And the link ID is the IP address on the interface of the designated router. And this is, the whole subnet is 10.0.0.0/24. So this just happens to be the IP of router 4. And the same is true of all the routers, right? It'll be 10.0.0.1.2.3.4. There is the OSPF router ID. There's the age of that link state advertisement for the type 2 LSA, that network link state, right? And so this, when I said abstraction, this is what I meant when I said abstraction. So everybody becomes fully adjacent with the DR and fully adjacent with the BDR, but they do not become fully adjacent with anybody else. So router 1 is fully adjacent with routers 3 and 4 because 3 and 4 are the DR and the BDR, but it's not fully adjacent. It settles into the two-way state. So they're OSPF neighbors, but they are not fully adjacent, and there is a significant difference. The difference being is that neighbors stop in the two-way state, and this is a steady state. This is not an error. There's nothing wrong here. This is exactly what's supposed to happen, and it's a druther. So it's not the DR and it's not the BDR. From the perspective of router 1, he sees router 2 as a DR other. But when the election took place on the multi-access segment, 3 was elected the BDR, 4 got elected the DR, right? And so now let's do this. Let's go to router 4. And here's where the activity talks about that dead timer, interface fast Ethernet 00, and I'm going to say shut. Now, if I quickly transition over here to router 1, and I say do show IP OSPF neighbor. Well, that's funny. I'm still fully adjacent with the DR, but the interface is down. But what do you notice that's different in the dead time column? Exactly. And we talked about this in class. At layer 1, with a point-to-point connection, you're going to notice that you've lost connectivity immediately, and OSPF is going to react immediately because it's going to be notified by a lower layer of the stack, right? It's going to be layer 1, and then layer 2 is going to know it's down right away in a point-to-point link with those serial back-to-back serial connections. But here, we're plugged into a switch. And so the routers, just like the activity that we have, right? The routers that are plugged into this switch, if that interface goes down on router C, which is what we're being asked to do, I've started the debugs here, but let's do this. So on router C, if I were to go into global config and interface gig 00 and say shut, what's happening right here is, yeah, the switch knows it's down and router C knows that the interface is down, but B and A are just fine. Show IP OSPF neighbor, they think right now, and we've got to look at that dead timer value, they're thinking right now, hey, everything is fine, right? There's no big deal here. Until the dead timer expires, then you're going to end up with an issue, right? Like we did here. And we're going to have an election to see who's going to be the new DR and who is the new BDR. So if I say do show IP OSPF neighbor, you can see now that the new DR was the former BDR. So the BDR is promoted to DR immediately, and then there's an election for the BDR. And this goes back to why the BDR is elected first, because that's all that needs to be elected. When the existing DR fails, the current BDR is immediately promoted to the DR. And then we don't need an election for the DR because the BDR became the DR. So this is why the BDR is elected first. Like we saw, when we bring everything up, there's an election for the BDR first, then the DR. Because when the DR fails, The existing BDR immediately promotes himself to the DR, and then there's an election for what? A new BDR, right? And that's what I meant when I said OSPF has to behave the same way in the DR-BDR election process. So the BDR is always elected first. And you see in the reason of a failure, it makes sense. Because if the DR was elected first, the BDR is going to promote itself to the DR. We don't need an election for another DR because we have one. It's going to be whoever the BDR was. So that's why the BDR gets elected first. And so here you can see we've had a quick change in the topology, right? To where now router 2 is the BDR, router 3 is the DR. So if I was to kill the interface on router 3, who's going to become the DR? And I think we've already got it here. So if I was to say shut, right? Again, take a look. Router 1 thinks, yeah, no, 3 is my DR. But take a look at what's going on here. Look at that dead timer value, right? Very important. We've dropped below 30 seconds, which tells you what? We're missing hellos. And this is what I refer to as sort of the countdown to extinction, where now we're below 20 seconds. So we've missed 2 hellos. And that interface is down. So we are not going to have an exchange of any hello packets between router 1 and the DR. And so what's going to happen is you're going to see almost automagically here, the current BDR will immediately be promoted to the DR. There it is. And so if there were other routers on the segment, and router 1, the router I'm on, is the other router on the segment, and if I were to say do show IP OSPF interface, right? Who got elected as the backup designated router? Yep, me, because again, routers at this point is router 2 and router 1 are the only guys here, right? So back to our activity here. When we take a look at what's going on, it wants me to re-enable the link between router C and the switch. So I come over here to router C, and now let's say no shut, right? So router C is going to come back online after spanning tree works itself out here. But what you're going to see is no change at all. So whomever the current DR and BDR are, if I were to say show IP OSPF neighbor, so router 2 is considered the BDR, router 1 show IP OSPF interface, router 1 is considered the DR, right? Because this was the BDR before the interface on router C went down. And when the interface on router C went down, the BDR immediately promotes itself to the DR. And so take a look here. Do you see any kind of information? So here's the election, but we already know. The BDR is already router B. He stays the BDR. The DR is already router A. He stays the DR. And there is no promotion. There's no preemption of the DR status or the BDR status by router 3, even though, or router, I keep saying 3. When I say 3, it's C. Even though router C, do show run, has a higher OSPF priority, and it has a higher router ID. So it's got a higher router ID and a higher OSPF priority, but it went offline, right? And the reason that there's no preemption, like you would see with something like HSRP, where we saw that you would preempt, that if a router came back online with a higher priority, that it would preempt the current the active HSRP router and take over as active. With the designated router and the backup designated router, there is no preemption. Now, could you come up with a corner case of some kind that is absolutely bizarre where maybe there's preemption? I'm sure you could, right? And it does exist. I'm not going to get into it here, but it does exist. But it is so far removed from the realm of possibility in even a decently designed network that there's really no need to talk about it. So remember, it is not preemptive. So router C comes back online, and how does router A, or how do router A and router BC show IP OSPF neighbor? It's going to see it as what? Yeah, as a druther. It's just a DR other, because he's not the DR and he's not the BDR. He's just a druther. But because A is the DR, it's fully adjacent with that DR other, because A, which the router which we're on, is the designated router. And the same thing is true here. If I transition back here and let's go to router 2. Not router 2, I'm sorry, router 3. So we go to router 3 and I say no shut. And I'm going to go to router 4 and we're going to say no shut. And if I quickly say do debug IP OSPF adjacency, right, we may or may not see anything, and that's okay. And so we do, but take a look at what we're seeing. The DR BDR election, look at all the values that are being pumped out here. Yeah, 2 is the DR because he was the DR before 3 and 4 came back online. And he will stay the DR. And take a look at the final line that we get here. Who are the DR and the BDR? The BDR is router 1, the DR is router 2, because they were the DR and the BDR respectively before 3 and 4 came back online. So do show IP OSPF neighbor. And there we go. 3 and 4 are DR others because they are not the DR and the BDR. If I come over to 4 and I say do show IP OSPF neighbor, take a look at how 4 sees 3. They are now in the two-way DR other because you do not become fully adjacent. You're neighbors, but you are not fully adjacent. And so here's where we're going to talk about the abstraction. And we see the abstraction over here as well. Now, the abstraction is what the DR is providing. The DR provides that abstraction by flooding the type 2 LSA. And what the type 2 LSA does is it basically makes, and let me do this here, and this pen is kind of dying out on me here. It basically makes the multi-access segment appear as the pseudo node, right? Because remember, we talked about the pseudo node. That's literally what's happening here. Here's the abstraction, is it's no longer looked at as like, oh, we're fully adjacent with everybody. No, no, no. Everybody is fully adjacent with the pseudo node, the DR, right? So it's almost like it turns it into a star topology, because if this is my pseudo node, router A and router B and router C, who are they all fully adjacent with? Yeah, and if it was router D, fully adjacent with the DR, the pseudo node. That is who they become fully adjacent with. So the whole concept of the pseudo node and the designated router, and again, those terms are synonymous, it basically turns the multi-access segment into a point-to-point star topology in the context of the adjacencies, right? And that is exactly what's taking place. And so to go way back to the ARPANET, when the ARPANET first rolled out and you had the link state routing protocol, the majority, the overwhelming majority of the links on which the link state routing protocols ran were point-to-point links, which is why OSPF, in terms of its calculation with that shortest path first algorithm, it's expecting point-to-point links. And it's the designated router / pseudo node concept and implementation that basically abstracts the fact that these are not point-to-point links and makes them look like point-to-point links to the shortest path first algorithm. And that's what the type 2 LSA does. And really, when you look at the type 2 LSA, it's almost as if it's a summary, an intra-segment summary of what is going on here. Now again, you cannot summarize, and when I talk about summarization, I'm not talking about, oh, we've got 2/24s and we can summarize that to a 23. That's not what I'm saying. It's the topology summarization. So you can think of the type 2 LSA as a type 3 summary LSA, but it's the type 2 LSA, it's the summary, not of inter-area information, but of intra multi-access broadcast segments information. And here's what we mean by that. Let's go ahead, let's pull up the type 2 LSA. So if I say do show IP, OSPF database network, and let me guess, it's not going to let us see that. Show IP OSPF database network. Okay, it doesn't like it, but that's okay. That's why we're mirroring this activity here. Do show IP OSPF database network. There we go. So here is the type 2 LSA. And take a look at what the type 2 LSA gives us. It tells us the address of the designated router, just like you would see the advertising router ID, just like you would see on the ABR of a type 3 LSA. We get the network mask. And then, and this is the network mask, not of those router IDs, right? That's not what it is. It's the subnet, right? Because it's /24, the 10.0.0.0.2. And it tells us who is participating on the network. Here's a list of the router IDs. So from the type 2 LSA, all I need to do is look at the type 1 that has what? That type 1 router LSA that has the states of the links that these routers have, right? So I can see all that information. So really what we've got here is we have a type 2 summary of the multi-access segment. And that's the layer of abstraction that OSPF v2 is providing. Right? Now, again, it's not called the summary LSA. Type 2 is the network LSA. But when you look at it, right, it's really providing abstraction here. It's hiding the details that these are not point-to-point links from OSPF and the SPF algorithm. And that's really what's taking place. So back to the activity. And to wrap up, we were going to, it wants us to change. So let's change the priorities here. Well, the link between B, I think that link may have already been taken down. Let's do that real quick. So let's go into privilege exec global config interface gig 00, and we're going to say shut. And again, you're going to have that wait where we could go into the fast forward timer, which I believe is on the simulation tab, where you could do the fast forward. I usually don't do the fast forward timer, which is why I'm looking here. So it usually is there. Oh, playback controls. There we go. Capture fast forward. So you can fast forward if you want. We'll go ahead and let it die a death on its own. And that's where we see that the new BDR, so show IP OSPF neighbor, and we're going to have to wait here, I believe, a few more seconds anyway. Yeah, 3 more seconds. And then we'll see. There we go. And take a look. The BDR was elected as router 3. So 3 is elected as the BDR. So let's bring that interface up. So we'll say no shut. And the undebug, okay, good. So to change the DR and BDR, configure the gig 00 port on each of the routers with the following values. So on router A, we're going to go into global config interface gig 00, and I'm going to say IP OSPF priority 200. I'm going to go to router B, and I'm going to go into gig 00 and say IP OSPF priority, and I missed that. It was 100. And then on router C, we're going to say, going to global config, global config, IP interface gig 00, IP OSPF priority 1, right? So now A should be elected as the designated router, but here's the thing. we're going to have to clear the IP OSPF process, because simply setting the value is not enough to change. Remember, does the DR BDR election, is it preemptive? No. If it was preemptive when we made the change on A, right, and actually A was the DR, so it wouldn't have happened there, but on B would have become the BDR, and it didn't. And we can see that when we run the show IP OSPF neighbor command. Let's say do show IP OSPF neighbor. I believe 3 is the BDR, right? So what I have to do is I've got to do a clear IP OSPF process. So do clear IP OSPF proc. And this restarts the process, and we'll go in a round robin fashion here. Do clear IP OSPF proc. And then on C, do clear IP OSPF proc. And so ultimately what we should end up with, not do show IP OSPF proc, do show IP OSPF neighbor, is 2 becomes the BDR, 1 is the DR, and 3 is simply a druther. And again, we've got the 30 out of 30, but that's not the important thing, right? The important thing is understanding how the BDR process works, where the idea originated from, why we have it, why you hear the term pseudonode. Because think about it, if you had 15 routers on this multi-access segment, imagine the amount of traffic and the size of the link state database without the type 2 network LSA that is generated by the DR BDR. And so it makes great sense to demonstrate this for you. So I'm going to kick off Wireshark here, right? So you can see we've got Wireshark, and I'm capturing that entire VLAN on my side. So I'm going to say continue without saving. We're going to see some OSPF hellos, right? You see all kinds of cool stuff going on. Now let's do this. Now let's update. Let's bring router 5 online, and let's see how the DR comes into play in terms of the type 2 LSA. So we're going to go into global config. I'm going to say router OSPF, control U, router OSPF 1, and interface fast Ethernet 00, IP OSPF 1, area 0. Now, as soon as I hit enter, router 5 is going to begin multicasting hello packets out to try to find out, is anybody else out there wanting to speak OSPF? And there's going to be a flurry of activity here, so get ready. So you can see router 2 saw it and sent the database descriptor, and then there's the flurry of activity that I was looking for. You can see the link state acknowledgments and everything that goes on here, and I'm going to allow this to, there's some more link state acts, I'll allow that to stop, and that should do just fine, right? So now we're back to kind of just the regular traffic, the hello packets that we're seeing. But this becomes critical. Remember I said, you would have an incredible amount of link state acknowledgement traffic. And so actually, I'll go back up here. So here's where we started, right? Router 5 came online right here, and actually not right there. Where did he come online? It was a little bit before that. Here it is right here. So here's the first hello packet from router 5. Now, the reason I know that this is the first hello packet is because you can see it's getting sent out to 224.0.0.5, right? Which is, he is multicasting to the all OSPF routers multicast address, and basically saying, hey, hello, is anybody out there? I'm looking to speak OSPF. I want to talk some OSPF with you, right? And then 3 sending his hellos, and now 5 has heard 3. So he sends a hello packet unicast directly to 3. And then 2 sends a hello packet out, because remember at this point, 2 was our DR. And then 2 is responsible for sending the database descriptor packet over here, right? You can see 2 sends a database descriptor packet, does it again, and then we've got 5 sends his out to 1, to 2, 2 sends his to 5, and these are all these database description packets. But who does the link state request go to? The link state request goes to 5, right? And then 5 sends a link state request back to 2. So at this point, the DR-BDR election is already sorted out before we get to the database description packets, right? So now the conversation between 2 and everybody else is basically going to run through the DR, right? Or I should say between 5. 5 is the new guy. So the conversation between 5 and everybody else in terms of link state requests, right? So here's 5. He sends a database descriptor packet, right? But that's database descriptor packet. So here's 5. Link state update to who? To 2. Here's 5. Link state request to who? To the DR, router 2. So he's now communicating unicast to router 2. We come a little further down here, right? And why is 1 sending a link state request? Right, because 1 ended up as whom? Do show IP OSPF neighbor. Yeah, 1 is the BDR. And 1 needs to make sure that he is in sync with the DR. So information that 2 is getting as the DR, 1 needs to see that information as well. So 1 contacts 5, right? Here's 2. Link state update, right? Again, link state update from 5 to 1 because 1's the BDR. And so take a look here, 2 and 5, 5 and 1, 5 and 2, 1 and 5. And so this is the reduction of the duplication. Imagine if this was taking place between 100 routers and there was no concept of a DR. It would be insane, right? And so hopefully you can see, I mean, this is just 5 routers here, and take a look at the amount of traffic that's going back with the DR, right? And we have a DR. Think if we didn't have the DR. So again, 1 to 5, 5 to 1, we've got the updates, the acknowledgments. And here's 5, right, sending out to the DR, the 224.0.0.6, that's the all OSPF DR BDR address. He fires out a link state update, right? Because 2 knows who the DR and the BDR, I'm sorry, 5 knows who the DR and the BDR are at this point. And then 2, the DR sends a link state update out to everybody. Because now that all the updates have been taken care of between 5, the new guy, and 2, the designated router, the DR now sends out an update. And here it is. It's the type 1. You can see it right here. It's an update packet. Where are we at? Link state update packet. There's the originator, and it's going to all OSPF routers. And here it is. And it's the router LSA, right? Because this is, again, the reduction is everybody talks to the DR and the BDR on the segment. Whoops, on the segment. But in terms of the flooding of information, right, if this is my DR and this is my BDR, in terms of the flooding, all of the routers, you know, router X and router Y, they will flood their updates to the DR and the BDR at that 224.0.0.6. And that's what 5 is doing here. Hey, I've got an update. Sends it to the DR and the BDR, and then whomever is active as the DR, we only need 1 person to do it, he floods it to everyone. You see that? He floods it to everybody. And then who does everybody send the link state acknowledgement to? Let's take a look. 3 acknowledges to the DR and BDR via multicast. 4 to the DR and BDR via multicast. 1 sends it to everybody, right? Because it's the BDR. And then 5, who's a druther, he responds back. So again, he's not acknowledging to everybody, just the DR and the BDR. And so hopefully you see the criticality on a multi-access segment that OSPF is going to treat, right? It's going to get faked out, and it's going to treat it as if these were point-to-point links. And the way that that is possible, right, the abstraction of the fact that it's not point-to-point links, which OSPF is expecting, It's all done via the DR and the BDR and the Type 2 LSA, which you could think of, right? Think of it as, oh, it's just summarizing the information of the multi-access segment. And that pseudonode is virtual. Whoever's the DR, that's the pseudonode, right? And everybody's fully adjacent with that pseudonode, allowing OSPF to pretend that there are point-to-point links there so that SPF can do its calculation. All right, now I know that this was very in-depth, right, beyond what we talked about, but it's very, very important because the DR-BDR process is one of the most misunderstood processes and becomes very confusing for learners that are taking a look at it for the first time, or maybe, going back and trying to understand how the process works. All right, well, this is going to wrap up Packet Tracer Activity 10.1.1.12 on the DR-BDR. Thanks so much for watching, and I will see you for the final exam on Tuesday night.